Hello, I'm Dr. Harper. This video is an Operations Management BANA 3000 Spring 2021. This is a lecture video on inventory management. So let's bring up the notes. Now first in the notes, I start with the input-output model of you acquire items from your supplier and they go into your inventory. You distribute items to the customer, that decreases inventory. So the acquisition will increase inventory, distribution will decrease inventory. First, I start with some definitions. There are different types of inventory. Primary types of inventory are raw material, work in process, finished goods inventory. Now, these three are the primary types that are well known and usually referred to first. Raw material is the material before they create a product. The finished goods inventory is the final product. And the work in process is the partially made products and the inventory before the raw material before it's completed for a final product. And so that's called WIP, the WIP inventory. And if you have an inefficient process, the WIP inventory can be very large. Then you have component inventory, distribution inventory, and that is inventory that's on its way to the customer. Then you have two very important types of primary inventory, MRO, maintenance, repair, and operations, and M&S, material and supplies. Now the MRO, maintenance, repair, and operations, that has to do with things to keep things running, keep things going. The maintenance, repair, such as equipment, such as the material that is required to repair or to run things. But M&S is material and supplies. And material and supplies usually are things that are used up, like paper and paper clips and different types of inventory that is used on a continual basis. And usually these are referred to as staple items, and they have very low value as far as price point is concerned, but they're important to keep things running. Now the MRO quite often they could include expenditures of equipment in facilities or upgrade of facilities. And so these are usually larger ticket items. The M&S are smaller ticket items as far as price point is concerned. Secondary types of inventory, spare parts inventory, warranty inventories, returns if you have a reverse supply chain, research and development, quality control, promotional items, and there's all different kinds of secondary inventories. We are just going to focus primarily just on finished goods inventory in this introduction, in this inventory management, this first lecture, this first introductory foundational lecture. So what's the purpose of inventory? Well, the purpose of inventory can either have a routine policy or a transient policy. A routine policy to satisfy your demand is something called your lot size, your order quantity, your cycle stock. In other words, if you have a demand of 100 automobiles this month, then your lot size, your order quantity, your cycle stock will be, I'm going to order 100 automobiles to satisfy that demand. Another one will be safety stock, buffer stock, reserve stock. This is another routine policy to protect against stock out. And if you recall in another video, stock out is defined, I define stock out in my lectures as when you have demand on a system, but you don't have inventory to meet that demand, that's referred to as stock out. So stock out, I do not define stock out as zero inventory. It's zero inventory with demand, but you do not have inventory to meet that demand. That's referred to as stock out. So to guard against stock out, to protect against that, we have something called safety stock, buffer stock, reserve stock. They all mean the same thing. But all three of these really are referring to a routine policy to have extra inventory to guard against the likelihood or probability of having stock out. Another purpose would be transportation inventory, pipeline inventory, and this is routine policy to satisfy logistical requirements. In other words, if you have a very long lead time, that's going to have your inventory. That's going to be referred to as inventory and has to be counted as inventory depending on how the pipeline inventory or transportation inventory is handled, who owns it. And then you have anticipation or seasonal inventory. These are transient policies to respond to known or forecasted demand. And for example, if you have a seasonal demand, Well, the transient policies to change up and down, increase and decrease to satisfy the seasonality of your demand would be a seasonal inventory. Anticipation inventory, on the other hand, is you anticipate a storm coming because you have the forecast, you know it's going to happen, so you're going to anticipate a need for more inventory. Another transient policy is speculative or hedge inventory. These are transient policies to respond to unexpected demand or critical inventory. In other words, you can speculate that something might happen, but you don't know. So you're speculating that something might happen here in the near future. And sometimes R&D, research and development, how industry is going or your product is moving or maybe transitioning, you're going to speculate that you might need more inventory. And so that's more of a prediction. Now, hedge inventory could be you're hedging for, say, critical inventory, that you want to make sure that the risk of running out of inventory, the risk of stock out is so great, you're going to hedge that by having critical inventory and having inventory to guard against it. For example, pharmaceuticals or drugs or medical supplies, because if you don't have that, then people will die. And so the risk of stock out is very high, and so you have to make sure you do not have that situation. Metrics inventory, how do you measure it? Well, there's different measures. We will look at measures in this lecture. Aggregate performance with inventory turnover rate, and we'll define that. And that'll be a demand rate over the inventory carried, and we'll define that and calculate it. And then inventory supply is really just the inverse of that. We will not go into the inventory supply metric, but we look at the inventory turnover rate metric. And then you have effectiveness of inventory. Now, I put this in this lecture because there is no one measure of effectiveness. It really depends on the industry, the company, the inventory, what they're interested in, where their strategy lies. And so you can have all different kinds of metrics to measure the effectiveness of current inventory. You can measure inventory that's being shipped or received, how many orders were placed, how many items were shipped, or the dollars that were coming and going, if it was received or not, that's quality. If it was on time, quality, or other measures of quality, like customer satisfaction, for example. So there's all different types of metrics to measure effectiveness. Classification of inventory. We will look today, actually we will look when we'll do an MRP, different classifications of inventory. High SKU values would be A items, low SKU values would be C items. Well, SKU is an acronym which stands for Stock Keeping Unit. A stock keeping unit is just a unique identifier of an inventory item within an inventory. You might have 100 books. They're the same books, but it has one SKU item, but that SKU item might have 100 items within that SKU item category. So the A items are high value SKUs where that book might be extremely expensive or it may be very, very inexpensive. An inexpensive price point would be a C item. An expensive price point would be an A item. Counting inventory. You can have periodic full inventory counts from the beginning to the end and count everything, or something called cycle counting. You have partial inventory counts throughout the year. For example, divide your inventory up into fourths, and every quarter count 1/4 of it. So over the year, you've counted all the inventory, but you simply didn't count it all at the same time. And then cost of inventory. We'll be using cost in this lecture. The three costs that we'll be looking at are carrying or holding cost. And these are unit carrying cost. The big C is cost, the little c is carrying. I'm using the word carrying. Some people use holding. Instead of C sub C, some people use a big H for holding cost. And that is when you receive inventory from your supplier, you're holding it, you're carrying it in your inventory. That costs money. And then the ordering or setup cost, again, C is cost and little o is ordering. This is ordering it, placing an order. This is your purchasing department. How do you place the order? People who place the order, the computers, the overhead, and everything in placing the order. Or setup. And sometimes the setup cost for manufacturing, and you have a requisition for manufacturing production, that costs money to actually cause inventory to be created. And then the item or acquisition cost, this is just the cost of the item, the price point of the item, it's the cost of the item. And then you have shortage cost. We will not look at shortage cost in this lecture, but I put it in here to be complete. If you have stock out, what do you do? Well, you can have back orders. You can have buyout. You can have a back order cost here. And in different courses that I teach, I will actually use the back order cost to see how it is applied to stockouts. But not in this course, not in this lecture. Now, finally, 2 fundamental questions of inventory theory. The lot timing question, when do you order? When do I place my order? And the lot sizing question, how much do I order? So those 2 questions I call the 2 fundamental questions of inventory theory. How much do I order and when do I order it? And that's what we'll look at today. So inventory management will start with having your forecasted demand, having your cost, and then saying, how much do I order and how often or when do I order it? Now, this information over here is a summary of what we will be covering today. And this will be in the homework. So, before I get into it in too much depth and detail, let's look at an overview here. Here's what I'm going to be covering in this lecture. An inventory policy contains 2 fundamental questions of inventory theory. How much to order? A lot sizing question, or the quantity ordered from the supplier. And when to order? A lot timing question, or when to order items from the supplier. So I'll be developing this in three steps. First, the fundamental relationships. And notice here I have T equals Q over D, where Q is a lot size Q, order quantity. D is your demand rate, and T is something called inventory period, which I'll define in the next page. Or I can solve this equation for Q and FQ equals DT. Notice the first one is an inventory period, which is time. That's when to order. Q is the order quantity. That's how much to order. So I'll first start with this fundamental relationship. And this fundamental relationship will define terms, but also it defines concepts and relationships that are going to be very important all the way through all the lectures. Next, we focus on when to order with a reorder point, where we have demand, but then lead time is when you place the order and receive the order. That's called the lead time, which we'll define. And then SS is safety stock. And then we focus on how much to order with EOQ. EOQ stands for economic order quantity. And this is a lot size which minimizes cost, the cost of ordering and the cost of carrying. And here's your demand. This is the square root function, and so or square root operator. And so the Q, which will minimize your costs of carrying and ordering added together, is called the economic order quantity. Then, that's the first stage in the three steps here. The next, I'm going to represent an inventory policy 2 different ways. In a continuous review system with ROPQ, when to order, how much to order. In a periodic review system, TQ, when to order, how much to order. And notice how much to order both have Q, but when to order, and there's where the change is between a continuous review system, periodic review system. So this is what we're covering in this lecture. Now, a follow-up, an extension, would be stochastic demand, or stochastic lead time, or stochastic demand and lead time. So the idea here is that what if the demand and the lead time is not constant? What if it's a random variable? Then how does it change? We're not going to cover that in this course, but this is where this theory has extensions. This is where the theory is extended to. Okay, now let's come back, compare it. Let's start with the fundamental relationship. Here we go. Okay, first of all, the fundamental equation, Q equals DT. Q is a lot size or order quantity. D is your demand, and initially it's going to be a constant demand rate. T is called the inventory period, which also means the time between orders. So that's going to answer the question, when do you order? T time periods. If T equals 1 week, then you order once a week. If T equals 2.5 weeks, you order 2.5 weeks. And then ROP is a reorder point. Now, reorder point, what do you mean by point? Is the point of your inventory at which you reorder your order lot size Q. And we will define that here. But I'll take the QDT and the fundamental relationship, the fundamental equation. The fundamental relationship is QDT right here, Q equals DT. Okay. Now, as I develop this, I'm going to first start with an example for the quantitative part, the continuous and periodic review system, and then I go into the relationships with graphs to explain the relationships. And then I pull out other types of extensions or tangential developments. Okay, first of all, let's come back because QDT, constant demand. Suppose our demand has a constant rate of 1,248 items a year. It's a constant rate, so it can be prorated. I can divide that 52 weeks in a year. I get 24 items a week. 1248 divided by 52 is 24. That's given. Also, the lot size, let's say, is 312. The inventory period is 13 weeks. Well, do all three of these go together? The demand, the inventory period, and lot size? Yes, it does. Therefore, the QDT equation equals 312, the lot size Q, equals 24, the demand in weeks, 24 items a week, times 13, which is the inventory period in weeks. And notice I have 13 and 24 because 13 is in weeks and 24 is items per week. So the time units on these two must be the same in order to get the correct answer. Now also, suppose our reorder point is 0. In other words, when the inventory reaches 0, then you place an order for, what's order lot size? It's 312. So when our inventory level drops to 0, we order 312. So the way this is represented first in the continuous review is ROPQ. ROP is 0, so I bring that down, and Q is 312. So the inventory policy for continuous review is ROPQ, or 0312. And often in industry, they will say my inventory policy is 0312 or 10200. What does that mean? Well, my reorder point is 10. My lot size is 200. My order quantity is 200. Or it's 25, 3000. So, or 500, 600. And so the ROP is one value, and then the Q is the second value. And so that's usually, when you have two numbers like that, then that indicates, in this course anyway, the continuous review inventory policy, where the first number is the reorder point and the second number is the order quantity. The periodic review. Well, the periodic review is a little bit different. The lot size is the same, but the first number is the inventory period, and that's going to be a time. That's the time between orders. So the ROP tells you when to order, when it reaches 0, but the periodic review system tells you the time every 13 weeks place an order. And what you place is 312. So every T time period order Q, or every 13 weeks order 312. So these are the two ways that we will express an inventory policy. So let's look at the Sawtooth Curve. To represent the Sawtooth Curve is the classic way to represent the fundamental equation Q equals DT. Okay, notice here's time along here. These are our weeks down here. And at time 0, we receive Q equals 312. This is our inventory level. So 312, this is our lot size. That's our inventory. Then as time goes by, our demand rate is 24 items a week. That's the slope of this line. So demand will take items out of our inventory, which over time our inventory begins to decrease. When it reaches 0, which is a reorder point, then we will order and receive another 312, and it goes away, and then another 312, another 312. And so this represents the inventory level with the Q equals DT curve. So when you look at this, it has the maximum up here is going to be 312. The minimum is reorder point. The slope of the line is the inventory demand rate, 24 items a week. And the interval between when we receive or place these orders is 13 weeks. That's our inventory period. So that's the interval, 13, 13, 13, 13. Okay. So that just illustrates the concept of the fundamental relationship of inventory theory or inventory management. But from this, let's go a little bit deeper and consider two definitions for this Sawtooth Curve. Suppose we have an annual planning horizon. In other words, we're looking for the whole year. Well, notice this is 52 weeks. Well, 52 weeks is a year. So this is 1 year. So over this year, how many times did we receive and use up an order? Well, we did it 1, 2, 3, 4, and that's called the order frequency of this inventory policy. So the order frequency from the Sawtooth Curve is 4 per year. So the annual order frequency is 4. Notice we have time related to it, and that time is in the denominator. So we have 4 per year. Now and notice our inventory period is 13 weeks. Okay, well, time units are going to be very important in this course. Very important, essential, because we can go back and forth between weeks, months, quarters, and years. And the time standard is 1 year is equal to 4 quarters. 1 year is equal to 13 weeks, or 13 months. And 1 year is equal to 52 weeks. So we'll always use that time standard. So if you have 13 weeks, notice 13 weeks is really 1/4 of a year, which is really 1 quarter. So units are important. Language is important. So if I ask you, I say, what's the inventory period in weeks? Then the answer is 13. But if I said, what is the inventory period in quarters? The answer would be 1. And then I said, what's the inventory period in years? What's the annual inventory period? It's 1/4. So 1/4 of a year represents an inventory period. So it's sometimes it's easy to make the mistake of, 13 weeks is there's 4 of them in a year, so the annual inventory period is 4 because there's 4 in a year. No, it's 1/4 of a year because there's 4 in a year. So be very careful with the language. But notice if it's 1/4 of a year and the order frequency is 4 a year, notice the reciprocal relationship between the annual order frequency is 4, the annual inventory period is 1/4. They will always be reciprocals of each other when the time units are the same. So the frequency is a reciprocal of the periodicity, and the periodicity is a reciprocal of the frequency. And notice I said the word periodicity, because periodicity, that's another word for this. It's the periodicity that keeps repeating and keeps repeating. We saw that in time series analysis and forecasting, because this is a time series. Okay, but now we can take the fundamental equation, Q equals dt, use these relationships, and in place of t, here put 1/f, and now we have 2 different versions of the fundamental equation. So initially, I said the fundamental equation is Q equals dt. But if I say the fundamental equation equals Q equals d/f, it's the same thing. So, because these are identities. So I can say the fundamental equation, but I can be referring to either one or both of them. Okay, but then I can solve for t and solve for f and have equations and have, again, definitions of the inventory period and order frequency. So these relationships we'll use in here. The second thing closely related to this is called the inventory turnover. This is the second important derivation of this development. First of all, the inventory turnover. The definition of a turnover, inventory turnover, is inventory that has come into your inventory and gone out of your inventory. For example, look at the first quarter here. At the beginning of the first quarter, we received 312. At the end of that quarter, we went to 0. So 312 came into the inventory and 312 went out of the inventory. So therefore, for the first quarter, our turnover was 312. Well, if we had 312 at the beginning of the quarter and then halfway through the quarter, and this is a constant rate, so a half of 312 is a 156. So what's the turnover? So if 312 came in and halfway through that quarter, 156 went out, Well, our inventory turnover is 156. So even though 312 came in, only 156 went out. So 156 came in and went out, but 312 came in, but only 156 went out. So only 156 of that 312 really went through or turned over in our inventory. So you can order all the inventory you want, but the turnover says how much came in and went out of the inventory. How much did we turn over and onto the demand? Closely related to turnover is, and in this case, notice I say that's equal to demand, my demand, because there's no negative inventory and there's no zero inventory. So therefore, the demand rate in this course will be the same as the turnover. Not always, but in this course, I'll make sure all the problems, it'll be easy to look at it that way. Because the demand is going out. And if we never have unfulfilled demand, then the turnover, if the demand is always met, if we never have stock out, then we'll always have the turnover rate equal to the demand rate, because we'll always have inventory to satisfy demand. So close related to turnover then is something called the turnover rate. And that is expressed as the turnover, the demand, the turnover, divided by Q over 2. Well, what is Q over 2? Well, we start with Q and we end with 0. And remember, to get the average inventory, we have the beginning inventory and the ending inventory. We add them together, divide by 2. Well, 312, the beginning inventory Q over 0 is just Q. Divide by 2 is Q over 2. So Q over 2 represents the average inventory in an inventory period. So for this simple example, then this is going to be the definition for this example, and most everything we do in here. Now later we'll be adding safety stock, and then things will change. But then I can do some algebra here, and 2 times D over Q. But notice D over Q up here is the same as the frequency. And so I have an identity here. The turnover rate for this simple example is 2 times the frequency. And notice frequency now has time related to it. And so therefore the turnover rate will have time related to it. What's the turnover rate per year? What's the turnover rate per quarter? What's the turnover rate per week? Okay, so these are definitions, and we'll be getting into these here in the homework. Okay, moving on here. The next is the ROP, when to order. Okay, let's come back up here. So now we had the fundamental relationships. Now we go to when to order, ROP. Okay, now let's do that. There we go, ROP. So now the equation is demand times lead time plus safety stock, where I have my QDT relationships, but I'm adding 2 more variables. LT is a lead time. Lead time is a time between when you place an order and you receive an order. Well, you're very familiar with this. When you order something, like from Amazon or something, and you order something today, and they'll tell you, or from a mail order catalog or something, they'll say, oh, it'll be delivered in 2 weeks, or it'll be delivered by this date or something. Well, the time between you place the order and receive it, that's called lead time. That's the time leading when you place it. It's leading when you receive it, okay? And then we also have something called safety stock we've already defined. It's the stock that you carry to guard against stock out. And so the relationship here of ROP, the reorder point then is demand during lead time plus your safety stock. That's the equation. But notice what this says. Demand times lead time. Well, demand is items per time, and lead time is time. Well, DT is the same. D is demand per time, same here. But this T is the time between orders, and that's why that's the lot size order quantity. The lead time is the time between placing an order and receiving an order, and that's defined as the ROP. Now the safety stock, we're adding this in to guard against stock out. Now the concept of this equation we will get into down here in the graphs. But before we get there, let's just go through some examples. Let's go back to the demand of 1,240 items a year, 24 items a week. Given the lot size of 312, inventory period of 13 weeks, And the QDT equation is given to be that. This we did the previous page. Now, let's go into the ROP. So now, let's suppose our lead time was 3 weeks. Therefore, the ROP for a safety stock of 0, then the demand is 24 items a week. The lead time is 3 items. Let's do it this way. The demand here is 24 items a week. The lead time is 3 weeks. And the safety stock is 0, so 72 is my reorder point. But what if my safety stock was 10? Well, my ROP then will be 24, demand rate is 24 items a week, times my lead time of 3 weeks, plus my safety stock of 10, which is 82. So depending on my safety stock, I can either have a ROP of 72 or ROP of 82. So for the continuous review, remember it's ROPQ. So when inventory equals ROP, order Q. That's how the continuous review inventory policy is interpreted. So for a safety stock of 0, the inventory policy is when the inventory level reaches 72, order 312, or 72,312. For a safety stock of 10, the inventory policy is when the inventory is 82, order 312, or 82,312. So we have two different inventory policies here, 72,312 and 82,312, depending on the safety stock. Is it 0 or is it 10? Okay, the periodic review, remember, is just TQ, where every T time period is order Q, where T is the inventory period. So in this case, our inventory period is 13 weeks. So the inventory policy is every 13 weeks, order the lot size or order quantity of 312, or 13 weeks 312. So notice when you have an inventory policy that's two numbers, it's continuous review. When you have an inventory policy where the first value is time, you have a periodic review. Okay. So let's see how this, the concept and relationships from graphs. First, we have the Sawtooth Curve here, the safety stock of 0. And so here we have our 312, and it comes down to 0, and it comes up to 312 down to 0. So our safety stock is 0. Now the demand rate is 24 items a week, right? So as we come down here, every week it drops by 24 because the demand rate is 24 items a week. Every week it drops 24. So let's look at this 13 weeks right here. At 13 weeks, my inventory level is 0. So if I back up to week 12, how much inventory will I have? Well, I have 24. Because in 1 week, the 24 goes away, it goes to 0. So if I go back 1 week, it's 24. If I go back 2 weeks, well, 24 and 24 is 48. If I back up 3 weeks, which is the lead time, my inventory level is 72. And that's why we have demand times lead time, 24 times 3, because that's the inventory level that corresponds with 3 weeks before 13, before it is time to reorder. So, and then the safety stock is 0. And so that's the concept. So we're back ordering, essentially. We're backing up and saying, what is the inventory level that corresponds with 3 weeks, the lead time, before when I place the order? Okay, and so it's going to be there is 72, and so you have 312. And you continuously review the inventory level, and when that inventory level goes 300, 250, 260, when it hits 72, bam, place an order for 312, and then it goes up. Okay, so you keep watching. When it hits 72, order 312, and 3 weeks it comes in, goes up to 312 again. So that's the concept. Now notice when this comes all the way to 0, if for one reason or the other, we're assuming constant rate demand. Now, what if the demand was not constant rate? We don't know. We're assuming that. What if we had more demand in the lead time than we expected? If the demand exceeds the inventory during lead time, then we will not have the inventory to meet that demand and that stock out. Well, the probability of having stock out is called the stock out level. And I say that down here. the stock out level of an inventory policy is the probability of having stock out. And I call that alpha. So alpha represents the stock out level, which is a probability. Well, we're not going to calculate it in this course. Other courses I do, but in this course we won't. But the idea here is understand the concept. So if you have a very high probability of stock out, higher than you want, and you want to decrease the probability of having stock out, decrease the probability of running out of stock, then a logical approach is increase your inventory. But what do you increase? Well, you increase how much inventory you carry during that lead time. Because once it's 72, you place your order. And then during that lead time is when you're looking, the demand during the lead time is what you're concerned with. If the demand during the lead time is insufficient, if the demand is greater than the inventory, than the ROP, then you'll have stock out. So what people do to guard against that is just carry something called safety stock all year long. And so notice you have this little band here. And that band, theoretically, is my safety stock of 10. So this is my design. This is my plan. And that is I'm carrying 10 items all year long to guard against stock out. Well, when you do that, over here, the Sawtooth Curve, when you move from safety stock of 0 to safety stock of 10, everything just kind of shifts up. It just moves up. And therefore, this is 312. Now this becomes 322. This is 72, 312. This is 72 here, the reorder point. This becomes 82. The inventory goes this at the end of an inventory period, it drops all the way down to 0. This will drop all the way down to 10. So the average inventory here from 312 to 0 divided by 2 is 156. Well, the average inventory here is 166. So it just shifts everything up, but not everything increases. Two very important things do not increase. The inventory period is still 13 weeks. And the lot size is still 312. The lot size is still 312. And the inventory period is still 13 weeks, or 1 quarter or 1/4 of a year. And the reason it stays at 312 is because when this comes to 0 and jumped up to 312, this is 322, but it rises to 322 not from 0 but from 10. So from 10 to 322 is 312 again. So the plan, the design, the ideal, the assumption is it drops to 10 and then goes to 322, so my lot size is still 312. So to lower the probability of stock out will increase our safety stock, because the more safety stock we have, the more we have inventory to guard against stock out. If you're guarding against stock out, you're lowering the probability of having stock out. Well, the service level in this development will be defined as a probability of service of no stock out, or not having stock out. So 1 minus alpha is the probability of the service level. But notice, an easy way to remember this is that the service level then is directly proportional to the safety stock. If the safety stock goes up, the service level goes up. But the service level is inversely related to the stock out level. Because if you increase your inventory, your safety stock, then the stock out level goes down because it becomes less and less likely to run out of inventory. And so there's where in the analysis of service levels versus, and if you increase your safety stock, you're increasing your inventory costs. Okay, but you're decreasing your stock out costs. And so there's a break even in there. And so there's where the ROP theory goes. I was combining that with Eoq. So next, let's look at Eoq. So now let's come back to our design up here, our outline. So we've done the fundamental equation, we've done the when to order. Now let's go to how much to order and Eoq. Okay, 1, 2, 3. Eoq. Well, we've already had the fundamental equation and the ROP. Now, in order to do Eoq, I'm introducing two cost. I've already introduced these, but I'm introducing them again. the unit ordering cost, C sub O, the cost to place one order, the unit carrying cost, and now this is the cost to carry one item over a time period. Now this unit ordering cost that I want to emphasize here, it's the cost to place an order. It's not to order one item. A lot of people think, oh, it's how much it costs to order one item. No, it's how much to place one order. And that order could be for 100 items. Suppose the ordering cost was $50 to place an order. Well, I want to place an order. That order of $50 could be for one item, or that order could be for 100 items, it's still $50. That order could be for 1,000 items, it's still $50. So it's the cost for one order, not for one item. Now the carrying cost also has related to it the unit carrying cost has the items over the cost of an item over time. And so the cost, whatever it is for an item over time, let's say for a year it was $1 per year, but 2 items would be $2 per year. But one item for half a year is 50 cents a year, 50 cents for half a year. So you can prorate it for the number of items and how long it's being carried. Okay, and then the relationship is given by a square root of the 2 times is this equation here times my demand rate and the ratio of my ordering cost to my carrying cost, my unit ordering to unit carrying. So before I get into EOQ, for this course we have accounting, which is a prerequisite. You've probably heard of EOQ before. The EOQ quantity, the economic order quantity. But I want to emphasize that EOQ is not a quantity. It's a concept. It's a concept of a minimum cost depending on what system you're trying to optimize or minimize. And so to emphasize that, I have 10 different EOQ models here. Each one of these will have their own EOQ value. So EOQ is not just a value. The EOQ is a concept which will generate a value depending on which of these models you use, what's the system, what type of inventory you're applying this to, company objectives, etc. And I divide this up in demand. Constant demand, the basic EOQ model, that's what we'll do in here. Quantity discounts, we'll do that. Ending, I'll have one model just to show how this expands. We have continuous replenishment, planned back orders, we won't do in here. Stochastic demand, single and multiple period inventories, won't do that. Irregular demand, here are different heuristic models of least total cost, part period algorithm, part period balancing. And this is a dynamic programming problem technique that minimizes cost from multiple stages in a irregular demand. And so we will we'll look at irregular demand in the next topic in MRP. But for this development, just to understand the foundations and the basics, we'll be doing the basic model primarily. And then I'll show you the quantity discount as an extension, and that's all. So this is just an introductory course. That's all we're doing. Okay, definitions. C is a unit cost. C sub O is unit ordering cost, unit carrying cost. I can extend these to the total acquisition cost, let's say the demand over a year, for example. The total ordering cost, let's say the order frequency, say over a year. The average inventory over a year, say. So whatever these are, they're over some planning horizon. Could be over a year, could be over a quarter, could be over a month, could be over 10 years, however you want to do it. But the time units are going to be important to get the right values. If I add the ordering and carrying cost together, I call that the total inventory cost. If I add all three together, I call that the total cost. Okay, now what are the relationships? There's a bunch of equations floating around here. Let's get some concepts going here. Okay, first of all, let's look at this graph. Now this graph is say this is 4 quarters. The time here, suppose these are quarters. We have 4 quarters. So we have quarter 1, quarter 2, quarter 3, quarter 4. Well, now we can say the order frequency is 4. So here's 1 order, 2 orders, 3 orders, 4 orders. And the inventory level is 100. So if I take this order frequency of 4, 1, 2, 3, 4, and I put it right here times C sub O, I'll get my total ordering cost for this problem. But my inventory, my maximum inventory is 100, my minimum inventory is 0, my average inventory is 50. So if I take that 50 and put the 50 here, my average inventory, times my unit carrying cost for the year, I'll get my total carrying cost. So for this problem, I'll have an ordering cost and a carrying cost. I have those two costs. Okay, suppose I double this. I increase this to 200. So my lot size is 200. My order quantity is 200. It's going to last twice as long, so therefore my frequency drops from 4 down to just 2. So my ordering cost decreases. But since I'm carrying 200, my average inventory jumps from 50 to 100. My carrying cost, then my average inventory increases, so my carrying cost increases. So one decreases as the other increases. Conversely, I can decrease this to 50, and then my carrying cost decreases, my ordering cost increases. So when you have that relationship, which we saw that at the very beginning, the break-even relationship between if one increases, the other decreases, you can have a break-even in there to where you can have a minimum cost of these two added together. So we want a queue here, a lot size queue, that minimizes the total inventory cost, and that's going to be the minimum, and that's called the Eoq. So this is one way to conceive it, to conceive Eoq, economic order quantity, a lot size which minimizes those costs. So keep increasing and decreasing until we get the minimum cost. Another way is going to be in the graph down here, which is another way to look at it. But before we go on, let's find the Q. Okay, how do we find the equation for Eoq? Now consider this right here, this little box right here, I probably should shadow it. I think I will just shadow it. I'll put a shadow on it because you will not need to do this. But I do know, I do have students from time to time who've had calculus and want to know how would you derive that. I do have students who want to see the derivation. Okay, well, so even though you don't know how to do it, it's good to know what's being done. Know what's happening. So the total cost is the carrying cost, ordering cost, acquisition cost. The carrying cost is the average inventory times the unit carrying cost. The ordering cost is the order frequency times the ordering cost. The acquisition cost is just the total items, which is your demand, times how much those items cost. Well, I can put the average inventory for an equation, the order frequency for an equation, and the total items is my demand. Now I have an equation here, and I want to solve a Q here which minimizes the total cost here. So if I find a Q, notice this is the total cost is directly related to Q, inversely related to Q, independent of Q. So if I wanted to find a Q which minimizes total cost, I would use calculus. I take the derivative set equal to 0, solve for Q, and you have the answer. So in industry, if you don't know differential calculus, then you won't be able to calculate different types of Eoq models. But you just have to find someone who knows calculus. And usually there's people around who do know differential calculus or integral calculus. So if you do, find them. If not, for this simple example, I've done that for you, and Eoq equals that equation. So I bring it down here, and let's see how this equation is applied. So now let's apply it. Okay, first of all, let's suppose the demand is 12,480 items a year. Divide that by 52 weeks in a year, and I get 240 items a week. So let's suppose, given the unit ordering cost is $52 per order, every time I place an order is $52. My carrying cost is $1.20 per item per year. The lead time is 3 weeks. The safety stock is 10. So now the ROP can be calculated, demand times lead time plus safety stock. I have 240 items per week times 3 weeks, see, 3 weeks, plus safety stock of 10. And so my ROP is 730. Now the Eoq is a square root, there's my equation, the square root of 2 times my demand. Now notice my demand is in years. And this should be divided by 52. Because then this is my demand per week. No. So here's my demand per year. Wow. So these notes, I'm going to change it. So you'll see the notes that I'll post the notes with the right numbers in there. Okay, so this is a demand per year, 12,480. Yep, that's right. Items per year. I divide that. Times my ordering cost of 52. Oh, I got confused. Okay, shoot. It's a square root of 2 times my demand, which is 12,480, times my ordering cost here of 52. I thought that was 52 weeks in a year, but it's not. Okay, and then divide by my ordering cost, my carrying cost of $1.20. There we go. Okay, again, units are very, very important. You can see here I almost got confused. So me, you, everybody has to be very, very careful. Make sure that, so this is my demand. My demand is this per year. So this is going to be per year. And then my ordering cost is just per order. That's fine. My carrying cost is item per year. So if this is in years, this needs to be in years. So if I use that in years in the numerator, I need to use this in years in the denominator. So the years and the years have to be the same. So it's easy to get confused. So you have to go very deliberately and very carefully, because I almost got confused. And I've been doing this for decades. So it's easy to get confused if you go too fast. So you got to be not slow, but deliberate. I do the arithmetic and get 1040. And I'll do a lot of these calculations in the homework. So my inventory period then Q over D from our fundamental equations up there. My Q is 1040. My demand is 12,480, and notice that 12,480 is in years, so that ratio is in years. I can transform that to weeks, multiply that by 52 weeks in a year. I get weeks. Transform that to months. But you have to be careful. If you're transforming weeks to months, you don't divide by 4 weeks in a month, because there's not 4 weeks in a month. There's 4 1/3 weeks per month. So be very careful with the transformation. And I'll do transformations and conversions in the homework. Okay, and then I can actually, instead of Q here, I know my Q up here equals this. So I can put this in for Q. See? And divide by D. And so what happens is I have this equation for my inventory period. So this 1 month is my optimal inventory period. So there's different ways of doing it, and some textbooks will say the economic order quantity, which would be that. Some people call this the economic order period, which would be that. However you do it, it's all related through these equations. So my continuous review is my inventory policy of ROPQ is 730-1040. When the inventory equals ROP, reorder Q, or when the inventory is 730, order 1040. My inventory period is TQ, 1 month in 1040. Every T time period order Q, or every month order 1040. Okay. Now, let's look at the concept of EOQ from this graph right here. So the idea here, let's have 0 safety stock. The safety stock is 0. The total inventory cost then is the carrying cost plus the ordering cost, which is Q over 2 times C sub C, plus D over Q times C sub O. So I'm just using all those equations together. Okay? And so what I'm doing here is saying, okay, then Q over 2 is 1040 over 2, because 1040 is my EOQ. C sub C is 1.2. D over Q, and notice this is per year. There's my EOQ times 52, which is my ordering cost. When I do the arithmetic, notice I have 624 and 624. Here's why. Well, when I look at this line right here, this is linear in Q. So my total carrying cost here, which is linear in Q, is represented by this line right here. So this graph is where Q increases. This is Q. Here's my cost up here. So my cost here increases linearly as my Q increases, because total carrying cost and Q are direct related. And the slope of that line is Q over C sub C over 2. Okay. Now this line here, which is inverse, it's an inversed curve, is my ordering cost D over Q, as Q is in the denominator. So as Q increases, then the total ordering cost decreases. So this is my total ordering cost. When I add these two together, this is my total inventory cost. So you notice how this increases, this decreases, where they cross here is where that's a minimum. So visually you can see what's happening here. And that's why these two costs are the same. Because when these are the same, when these two cross, these are equal to one another, that means the sum of those are going to be a minimum. Okay. In other words, this right here, since it's a nonlinear function, this increases faster than this decreases, and this decreases slower as this increases. So when you move away from this, as you can see up here, when you move away from this, it's going to increase. It's going to increase both ways. So this is increasing and this is increasing. So and that's why. So this is the minimum cost, minimum total inventory cost. These two costs are equal, and the Q here, along this axis, the Q that makes all this happen is Eoq, where the total carrying cost equals total ordering cost for the safety stock of 0. Now, as it turns out, this is an extremely important concept, and it's a concept that drives a major portion of the lot sizing techniques in industry. And it can be very, very powerful and very, very clever. Okay. Let me give two examples. The first example is suppose you did not know what your unit costs were. You didn't know that. You didn't know that. You didn't know what the unit costs are. Okay? Let me put them back. But at the end of the year, you count up the total cost, so you'll know your total costs. You'll know what those are. Okay? And so here's your total carrying cost, here's your total ordering cost. Suppose the carrying cost was greater than the ordering cost at the end of the year. Financials, your financial statements at the end of the year. You say, oh, whoa, my carrying cost is more than my ordering cost. So is my lot size Eoq? No, because at Eoq they should be equal. But if the carrying is more than the ordering, then what does that imply? Well, on which side is, here's Eoq, on which side of Eoq is the carrying cost greater than the ordering cost? It's on the right side. So when the Q here, over here, the carrying cost is more than my ordering cost, when my Q is larger than Eoq. So when the Q is too large, my carrying cost will be more than my ordering cost. So suppose you know what your ordering cost, you know what your Q is, you've ordered it all these times. So okay, I've placed an order of 100 every time. Well, at the end of the year, if your carrying cost is more than your ordering cost for that item, the 100 is too big. Decrease it. How much? Don't know. But decrease it to 90 and see if it comes together. Then it go to 80. Then come to 50, goes the other way. Well, when the ordering is more than the carrying, that means the Q is too low. And then you can increase and decrease Q to where these come together. When they come together, that's Eoq. When these come together, the lot size which caused that to happen is Eoq. And so that's very clever. But that's the basis of the least total cost irregular demand algorithm. And a lot of consultants will use this in their consulting on small to medium-sized enterprises. That's one example. A second example. Suppose you did that. Suppose in this company you go up and down, you notice, okay. Suppose we did get Eoq, you know what it is. just for an example, let's say the queue is 100. If I order 100 items at the end of the year, then my ordering and carrying costs are the same. Well, good. Okay, if there's zero safety stock, then what's your unit carrying cost? Well, if my lot size is 100, and also let's suppose at the end of the year that this is $500. I have that's 100, and that's $500. So at the end of the year, you've placed 100 items. This carrying cost and ordering cost, both of these are $500. So if this is $500 and this is 100, well, 100 divided by 2 is 50. So if that's 50 and that's 500, that means my carrying cost must be $50 or $10 per item per year. So you can back out the unit carrying cost. And so this is how people will reestablish their carrying cost. So suppose you have 100 items. Suppose you have different SKUs in your inventory, and suppose you had 10 different SKUs in your inventory. 9 of those SKUs, the unit carrying cost was between $9.50 and $10.20, but that 10th item, the carrying cost was $300. How can that happen? It does happen. Why? Inefficiencies. Something is wrong in your warehouse with the carrying cost. So backing these things out then become effectiveness measurements on measuring how effective your inventory is and which inventories need attention. And there's where you do a Pareto analysis to identify inventories that need attention. What about ordering cost? Same thing. So suppose the ordering cost is $500, and you go back and say, well, how many times did I order? Well, you go to the purchasing department. You say, how many invoices do we have? Oh, we have 10 invoices. You did this 10 times last year. So they keep track of that. So if the ordering cost is $500, if this is 10, the order frequency is 10 over the year. Well, 500 divided by 10 is $50. My unit ordering cost is $50 per order. And you can identify, again, a metric on how the purchasing department, the buyers, with backing out the unit ordering cost. Backing out the unit carrying cost, looking at the warehouse and material management. Backing out the unit ordering cost is the buyers and the purchasing department. So you can actually measure proficiency and efficiency of those departments by backing these things out using this concept. And this is how people have good management with inventory management. Okay, now the carrying cost determination, remember, conversions are going to be important, but a very common, and this is kind of like an addition on how to represent carrying cost, because this is commonly used. And so you'll see this in almost every industry and in a majority of the companies. A commonly used expression for carrying cost, unit carrying cost, is unit carrying cost is something called I times C. Now this I here, okay, I'm going to do something here. This I here, there we go. I want to have a background of this I shade. Did it work? There we go. Okay. So this I here is arbitrary. I'm defining I here as a carrying cost. But the carrying cost is cost to carry $1 of inventory for a period. Now the C sub C, I've defined the unit carrying cost to carry one item of an inventory for a time period. Down here, the C sub C is $1.20 per item per year. Notice it's carrying an item per year. But the I is defined as the cost per dollar per year. And so this is a very common way of expressing carrying cost in many industries. That's why I'm talking about it. But the carrying cost per item is what's needed in the Eoq model. and all of our models, if we're using cost, if we're looking at cost, carrying cost. But the I is oftentimes what is used, is what is reported. So how do you convert back and forth between the two? Well, the conversion from an item to dollars is dollars per item, simply. So, for example, if an item costs $6, but it costs 20 cents to carry $1 of that item, but you're carrying $6, so 20 cents times 6 turns out to be $1.20 per item. And that's why it's I times C. Okay? Let me take that out. It's not doing anything. Okay. And so that's how these are used together. Why do we do it that way? Why do they do it that way? Well, the carrying C sub C then is the carrying cost per dollar times C is the carrying cost per item. And I also is a C sub C over I. The reason people do that is because quite often in accounting, you will express your inventory in dollars. You'll express your carrying cost in dollars. And so what is your cost per dollar? Well, you don't know what the item costs are sometimes within financial statements. You know the cost of your inventory, and you know how much inventory you have. You divide that, and you get the total carrying cost per dollar. So often the carrying cost per dollar is what's reported. And then, for example, let the demand equal this 12,480 items a year, ordering cost, carrying cost, this kind of thing. So you may not know what your cost per dollar is, or cost per item is, but you know the cost per dollar is just 20 cents per dollar. So then what you do, instead of the carrying cost of $1.20 here, it's 20 cents times the cost IC. And there's where this equation up here comes in. So it'll be right here in the denominator in EOQ. So the value of I can be determined from financial information, as I said. It's a total inventory carrying cost per year over the average inventory per year in dollars. For example, if the total inventory cost is $624, Q over 2 in our example is $1040. That's how many items times $6 per item over 2. That's our average inventory in dollars. Okay, so our EOQ is $1040. But then our item cost here is $6 per item. So $6 times all those items turns out to be, and divided that by 2, is the $3,120 average inventory in dollars. So the total inventory cost in dollars divided by the average inventory in dollars is 20 cents per dollar. So that's my carrying cost. And I'm calling that I, but it really is a carrying cost. It is a unit carrying cost. It's a unit carrying cost with different the different units. So always look at the units. Okay. So I have an exercise set here that you can go through onto what I mean by exercise, I give these values up here on how the different things, and then down here are the actual answers. Okay, just as an exercise. The last thing we're going to be doing in this lecture is quantity discounts. So here's the setup. Suppose we had an inventory item here that cost $125. Suppose we had a nice desk and it cost $125 from the supplier. So you go to the supplier and say, you know, I'm renovating the business school. I'm going to buy a lot of these desks. Okay, well, you know, depending on how many desks you buy, if you buy between 50 and 99 desks, I'll give you a 2% discount on that item cost. And I'll sell it to you for $122.50. Oh, okay. So if I buy more, then I can buy each of these items for less. Yes. And that's called a quantity discount. That's one version of quantity discounts, and that's the version we'll use just to introduce the idea. Because it does happen. So if you buy in large quantities, then they'll sell it to you for a lower price, as long as you buy in large quantities. and say, oh, wow, okay, that's good. That's just for the business school. The university over here on the campus, there's other innovations. Maybe we can work out a deal and buy even more. They says, well, if you have 100 or more, I'll give you a 5% discount on the item cost. And a 5% discount of 125 is 118.75. So, whereas before, when your lot size increased and decreased, the carrying cost and the ordering cost changed. Now, the item cost, acquisition cost, is going to change. So now we have 3 different costs that we're looking at, and those 3 costs will be changing when we change our lot size. So we no longer use calculus, we use an iterative approach. And so that iterative approach is a 4-step procedure. And these are the 4 steps, which what I'm going to go through right now. Before I do that, let's set some values. We have our costs here, okay, our item cost for the discounted cost. But to work the problem, let's suppose our demand is 200 items per year. Our unit ordering cost is $50 per order. And our unit carrying cost is 40 cents per dollar per year. Now I say C sub C in here. I could have deleted that, but I put it in to, C sub C, but I put it in just to emphasize that this is a carrying cost. It is a carrying cost. And I could have said carrying cost, the I is that. Okay? So in other words, don't be too concerned with variables. Look at the units. The units define what those variables mean, because these have all different names in industries and different textbooks. Okay, let's take these 3 values and let's work the problem. What is EOQ for this quantity discount problem? It's a 4-step procedure. Now down here below, here are the 4 steps. There they are. And these 4 steps, I'm going to go through each one. But down here are all the calculations for the step 1, step 2, 3, and 4. Here are all the calculations and determinations that go into the values in this table. Okay, first, let's bring the range down. Here's the ranges. Order quantities, there's my range for those quantities. There's the discounts, and these are the item cost. So those 3 columns I just copied. I copied these down to here. And there they are. Okay, whoops. And there they are. Okay. Step 1, calculate the initial Q for each category. Okay. Well, the calculations down here simply say, well, let's use the Eoq model. It's the initial Q. It's not the final Q, but we're starting with Eoq for each category. Well, for each category, we have the square root of 2 times my demand, which is 200. That's given up here. And the 50 is given. Okay, that's given. Now, and since I have different item costs here, I'm going to have different item cost in each of these categories. I go back to my cost per dollar of 40 cents per dollar. So here I have my 40 cents per dollar per year, 40 cents times my item costs. And so notice I'm using the IC version. And so the IC version of carrying cost is used in quantity discounts, because quantity discounts means the item cost is going to change. So when that changes, the carrying cost will change. Now that doesn't seem logical, but as it turns out in large inventories, it works out pretty well. Okay. When I do the calculations, I get 3 different values. I take those 3 values up here under step 1. I put them under step 1. I call that my initial Q. So there's my initial Q. So let me box that in because there's my first one. Boom. So now I'm done with that one. Now step 2 is called a feasible Q. So under step 2, if the initial Q is in the range, the feasible range for the category, then select the initial Q as the feasible Q. Okay. But otherwise, select the value in the range closest to the initial Q as a feasible Q. So let's do that up here. Okay, first of all, for category 1 here, the initial Q is 20. Well, the range for the discount is 0 to 49. 20 is in that range. Therefore, that 20, the initial Q, becomes a feasible Q. Okay? Category 2, I have 20.2. My feasible range for my 2% discount is between 50 and 99. 20.2 is not in that range. 20.2 is not between 50 and 99. It's below 50. So what do? Well, what value in this range is closest to 20.2? Well, it's 50. So 50 then becomes the feasible Q. Likewise for category 3, the category is 100 or more. 20.51 is below 100, so 100 becomes my feasible Q. So there's category 2. So let me box that in. So now I'm done with that. Okay. Now step 3 simply says calculate the total cost for each category. Okay. The total cost for each category. Well, step 3 down here, notice I'm going to have my carrying cost, my ordering cost, my acquisition cost. Well, the I is going to be the same for every category. The ordering cost is the same and the demand is the same for every category. The demand is the same for every category. But notice my C and my Q, the C is going to be the discounted cost. The Q is going to be my feasible Q on each one of these. So let's come back up here. So let's take my feasible Q now and let's shade it, because now this is becoming the Qs I'm going to be using. Whoop, let's shade all of it. This is the Q I'm going to be using, and then I'm going to be using these item costs. Let's shade that in. So there's the C I'm going to be using, the cost, and there's the Q I'm going to be using. And so notice my cost here, 125, 122.50, 118.75. That's exactly what I have for my cost here for the category 1, 2, and 3. My cost here for categories 1, 2, and 3. A big mistake people make is they don't put it in all the categories. Now what about my Q? 20, 50, 100 for my feasible Q? Well, there's my feasible Qs. 20, 50, 100, 20, 50, 100. So I calculate my three total costs for the 3 categories. I take those 3 costs, I put them up here under my total cost. Now, step 4 simply says which one's minimum. This is 26,000, 26,225, 25,925. There's my minimum cost, and there's my EOQ. So let's make this a bold. Boom. There's my EOQ. Boom. My EOQ is 50. Let's do it this way. My EOQ is 50 with a total cost of $25,925. Okay, so there's the EOQ. Now, that's the mechanics. Now, when we come down here to this graph down here, I'm just illustrating why this works. Again, to illustrate this with a graph. So here's how I do this. I'm taking in Excel, I'm taking my total cost here for the first category, that equation. But notice I'm letting Q vary between 10 and 150. And I calculate my total cost for each one of those. And I plot it. And that's category 1. There's the plot of the total cost. I do the same thing for the second category. I use 122.50 instead of 125. And I let Q vary between 10 and 150. And I calculated all of my second categories all the way down. Okay. In other words, if I move this out of the way, then here they all are. There's for category 2. I do the same thing for category 3. Okay. Well, notice category 1 is only between 0 and 50. So let's take 0 to 50. Let's bold that. So those points right there only refer to category 1, because category 1 will only be true for the 125. Because if Q is more than that, then category 2 will kick in between 50 and 100. But if my Q is more than 100, then category 3 will kick in. Then my cost will be there. Okay, let's bring this back. So notice I bold category 1 cost curve, category 2 cost curve, category 3 cost curve. So my order quantity, if it's between 0 and 50, that's my cost curve. 50, 100, that's my cost curve. More than 100, that's my cost curve. So which one's a minimum? Well, the minimum value of all of my costs is going to be there right there, which is 50, and that's why it works. Okay? And also this graph illustrates the concept underlying EOQ quantity discounts. And as it turns out, quantity discounts are very popular and used online. When you have online buying, purchase it through the website. Go online. Why? Because they have control of changing the discounts, changing the price, changes the order quantity. They have control of that. And prices can change. But historically, before the internet, you would publish a manual and send out the actual pricing manual, and that company had to abide by those prices. And they can send out a different manual, but it takes time to produce that book and send it out. But then it was binding. But today, now all the risk is going to the consumer, because now the seller, the company, can change these three values very quickly and very easily. Just prices subject to change, boom, they're changed, there they are. Now these are our prices. So this is equivalent to publishing a whole new pricing manual and mailing it out to all your customers. Well, now he says, no, come to the website, because now I can publish it in a moment's notice, depending on things that are the economy going fast and cost going fast. And that's why people use it. So quantity discounts are very popular, especially online buying and purchasing online. Well, that ends the lecture for for inventory management. There's more. There's a lot of extensions to this. I've mentioned a few of them, but this is a basis. If you understand this basis, understand this foundation, then that is a foundation you can build on very easily and very quickly. So this is all I have for the lecture. I hope this helps. And so between now and the next time I see you, be very careful out there. Don't take anything for granted.